I think we will get started. And good afternoon, everyone. Thank you for coming to ARB's research seminar series. Today, we're going to talk about formaldehyde from home central heating and air conditioning filters. So before we start, I just want to remind those who join us via internet, you can go to our research seminar webpage. There's the presentation slides can be downloaded over there, and also there's a link over there to get access to the final report. You will find more detailed information over there. And before I turn this over to our speaker today, I'm going to give a very brief introduction of this research. As you know, the research topic is about formaldehyde from home central heating and air conditioning filters. The PI is Dr. Hugo Destellas from Lawrence Berkeley National Laboratory. And why ARB found this research? Because we know formaldehyde is a known human carcinogen and toxic air contaminant with no safe level of exposure. And many indoor and outdoor sources can emit formaldehyde. For example, we have a regulation on composite wood to limit formaldehyde emission from composite wood product. But there are also some other indoor and outdoor sources can emit formaldehyde. We haven't studied very fully. So a previous study found fiberglass filters for commercial heating and ventilation and air conditioning system emit formaldehyde, but little was known about those used in residential systems. So this study was to quantify the contribution of residential fiberglass and the synthetic filters to indoor concentration of formaldehyde. With the results of this study, we are going to provide guidance to consumers and manufacturers and promote use of low-emission filter in residential systems. And for more information about ARB's indoor air quality program, you can go to the link shown on the screen and find out more information about our indoor air quality program. So today's speaker is Dr. Hugo Destellas. He's a staff scientist and the deputy leader of the Indoor Environment Group at the Lawrence Berkeley National Laboratory. And he has over 20 years of research experience focused on understanding the mechanisms of indoor air pollutants, reducing exposures to harmful chemicals, and developing technologies to advance healthy and energy-efficient built environments. And with all his excellent work, he published over 60 articles in peer-reviewed journals. And with that, I'm going to turn the presentation over to Dr. Destellas. Thank you.
All right, well, thanks very much, Soy, for the introduction, and everyone for being here today, and those watching on the internet as well. So, yeah, the presentation today is about a fairly limited scope of topic. It has to do with filters and how these filters impact our indoor air quality, and these are filters we use in our home. So I want to start by thanking Soy and also Peggy Jenkins, who have been really wonderful in managing this project and very supportive and really gave us great ideas and encouragement. My colleagues Tosh Hodchi and Brett Singer at the lab, and also our technical advisors who are listed here for also very important initial support and information. Particularly, I want to mention Thomas Justice, who also provided us with filters, samples that we could test, and Wenhao Chen, who did a really very thorough review of our final report. So let me start by saying, okay, why do we care about this? Clearly, indoor air is very important. We spend most of our time indoors. And the composition, the chemical composition of indoor air is quite different from the composition of the air right outside the window. And a number of things that we want to highlight here. The VOCs, the volatile organic compounds, which is the organic trace constituents of our air, are not only more numerous indoors, but also more diverse chemically. And the concentrations tend to be much higher, about 10 to 1,000 times higher usually with respect to outdoor air. Formaldehyde, which is the one we will be talking about today, is one of them, but a very important one. We classify sources, and this is just one possible classification, but I think one that is useful to understand, the nature of the indoor pollutants. The first group is what we call building materials, and clearly today's talk is about that. But I also want to mention activities. Our own activities generate also emissions that we need to account for, and at least here smoking and cooking and cleaning, and there are many other activities that we do. And then our own presence, the occupants themselves are a source of not only bioeffluents, but also the products that we wear, perfumes or shampoos or things like that, that also tend to emit chemicals. And finally, outdoor air is an important, in a way, is the baseline for all of the air that we have inside the building. We ventilate with outdoor air mostly to dilute a lot of our indoor sources. And if the air is polluted outside, that is the baseline of pollution that comes into our building. So if you think about formaldehyde, formaldehyde has been a focus for ARB and for a number of other agencies for some time. For a number of good reasons, it is a carcinogen. It also is an irritating compound for the respiratory system and the eyes and mucous. We find it in essentially every building we go when we do measurements, in both homes and commercial buildings, but it's typically higher in homes. And the levels at which we found it are usually higher than what we call reference exposure levels, which are concentrations above which there are effects that we want to prevent. So this figure here illustrates just from one recent study done by our colleague Bud Offerman. This was funded by ARB as well. These are about 100 homes in California, and the red curve is showing the very low outdoor levels for formaldehyde, just a few micrograms per meter cube, versus the blue curve, which shows the distribution of levels that are found in these 100 homes that go from a few ppbs to about 100 microgram per meter cube, or ppbs. We will use both units, ppbs or microgram per meter cube. They are, for formaldehyde, they are roughly almost the same scale, so it's easy to switch from one unit to the other. The median in this study in particular was 36 microgram per meter cube, or 29 ppbs. But you see the vast majority of the data lies above what is called the chronic reference exposure level, which is only 9 microgram per meter cube. And then a quarter of the data is above the acute reference exposure level, which is 55 microgram per meter cube. So it is a real problem. Formaldehyde is in all of our homes, vast majority of our homes, and it causes serious health concerns. I just mentioned here two more interesting features about formaldehyde. One is that it is very easy to measure, and that is one of the reasons why we have a lot of data about it. And also we can connect the dots between sources, exposure, and health effects. Perhaps there are other contaminants that can be more harmful, but if they are difficult to measure, we lack the information to make all those connections. So, and the other thing is that formaldehyde is fairly difficult to remove from the air. Once it is emitted there, most of the traditional air cleaning approaches don't work very well. You can't filtrate it very well. You cannot catalyze its oxidation very well. So it is a problem to remove. So that's why it's important to concentrate on the sources, understand which are the sources, and do the best we can to remove or at least to reduce their impact. One of the most well-known high emitters are wood products. And in part because these wood products it's not the wood itself, it's the polymers that are used to keep together the small pieces of wood that make up these composite materials that are these urea formaldehyde polymers. And that's why that has already been a very significant action on the part of the ARB to regulate those products. And I think it's a fairly successful program. And it's pretty much a de facto standard for the whole US, not just for California. But also other materials have the same polymers. Fiberglass containing insulation or ceiling tiles are materials in which the same polymers are used as binders. So that's why we are interested in this study to focus more on those type of materials. I just mentioned here the case of France just to illustrate that it's not only in California. I mean, a number of other countries are also taking initiatives in controlling and regulating wood products that emit formaldehyde as well. So how does it work from the chemistry point of view? These polymers are obviously a polymer. They are made of monomers or smaller molecular fragments that over the lifetime of the material tend to depolymerize or decompose. And that decomposition is catalyzed by the presence of moisture, water molecules. So the reaction is shown here in the slide. And there are a number of studies, and I'm showing here data from just one of them for about 2 decades ago, showing how, in this case, this urea formaldehyde insulation foam that is exposed to moisture in an accelerated way. And what these authors showed is that as you increase the level of moisture or absolute humidity, the amount of formaldehyde that is emitted increases. So that's one of the effects, the emissions of formaldehyde. The other effect is more structural. If you have an insulation material, you need to have all these big pores to keep the air sort of bubbles inside, and the degradation of the polymer actually breaks down the structure of the insulation. So even from that point of view, the material fails, apart from generating harmful emissions. So what we did in our group a few years ago was to study fiberglass filters that are used in commercial buildings. And these are different from the ones we use in our homes. They tend to be thicker and larger. And in this particular study, what we did was we used an unoccupied building that had 2 different zones. Each zone was serviced by an identical HVAC system. So we were alternating fiberglass and synthetic filters over several weeks and measuring formaldehyde in the space at moderate 50% humidity and also at 80% humidity. And what we found, and it's shown in the figure fairly clearly, is that in every case, the presence of a fiberglass filter increased the concentration of formaldehyde, and that increase was much more significant when the humidity was higher. So those 2 effects, the presence of a fiberglass filter and high humidity, are the 2 factors that led to an increase in formaldehyde level in the order of 5 to 10 parts per billion. So it was quite significant. So the question that led to this project that I'm going to describe now is, okay, we saw that for commercial buildings. What about the filters we use in our homes that tend to be a little thinner and smaller? So here's our study. First, we convened our project advisory committee, 5 members from industry, academia, and government that gave us really very important support and information with a lot of things we didn't know at the beginning of the project. For example, a couple of things that I highlight here. These fiberglass filters used in home tend to be on the low cost, low efficiency end of the market. So these are mostly used to protect the equipment rather than to filtrate air from particles or from pollution. And that is important. So that is something relevant to know, because it has to do also with accessibility and cost and other factors that were not part of our initial experimental design. So another interesting aspect is that the emissions of formaldehyde had a lot to do with the process by which a filter is manufactured, and in particular the curing process. So, and we will see some examples along the way. I'll highlight that as we go through the slides. We found that the same filters, for example, emit differently as they age in our lab. So the filters don't come, once you open the box, they're not always a constant source. The source strength continued to evolve over time. And we did some evaluation of that as well. Not every polymer used in these filters is the same. We are focused mostly on urea formaldehyde, but there are other polymers, such as phenol formaldehyde, for example, that tend to be lower emitters. And also we ask, okay, where should we not look at? I mean, what are things that you don't expect to be high sources? And the answer was, well, HEPA filters and also in general high efficiency filters are not expected to be high sources. The frame and the material that kind of is used for the structural part of a filter is not supposed to be a source. And the tackifiers, these are oils that are applied over the surface of a filter to make it to facilitate the arrestance of particles. That is also a material that is not supposed to be a source. So based on all of this information, our criteria for selection of filters was as follows, as shown here. One is it was recommended to us to look at all the three manufacturers. At that time, there were 3 manufacturers of fiberglass filters. I believe since then there was some consolidation in the industry, and now there are probably 2 only. But we did look at those 3 manufacturers. We also included synthetic filters, which are, like in the case of our previous study, these are used as reference because the emissions here are much lower. And also, as I mentioned, one of our committee members was kind enough to facilitate us access to filters that came directly from the manufacturing line, so did not go through the whole retail process. And that was very interesting for other reasons. So here's a list of filters that we collected initially. These are all purchased mostly online, majority of them through Amazon.com and other retailers. You see we have 4 different manufacturers, 3 of them for fiberglass and 1 is repeated fiberglass and synthetic, and essentially we had 2 different sources for synthetic filters. The MERV rating for fiberglass is fairly low. In most cases, it's about 4 when information is available. And synthetic filters tend to be much higher efficiency. For the filters that were sent to us directly from the production line, majority of them were fairly recent production. So it was good to see how were those emissions, which, we did for filters that were mostly freshly done, freshly prepared. Okay, and now let me describe our experimental approach, which had 2 parts. We ran most of these filters through what is shown here, which is our bench scale testing system. And then a subset of the filters tested here were then also evaluated in a much larger room scale chamber. So for the bench scale apparatus, what we had was this 200-liter box in which we would place a filter, we would introduce clean air, in which we could adjust the humidity by adjusting the flows on a dry and a humidified flow to the level of humidity that we set for the experiment, and then air would be injected at the bottom of the chamber. The air would be then running from the bottom to the top, and then exiting the chamber from the top on the opposite extreme from where it entered. We had 2 sampling ports, upstream and downstream, and samples were collected simultaneously on both of them. And certainly we had a temperature and relative humidity sensor to determine those parameters. The heating plate on the bottom had simply the effect of mixing. We were heating at just a degree or so above the room temperature, so producing some internal convection mixing. That was the only reason for that. Here are a couple of photos. You see there was a cover with all the inlets and outlets, and you see the, let me see if I can use a cursor here for this. The inlet had this long tubing that would bring the air to the bottom of the chamber, and then the filters were placed somewhere in the middle, and then air was coming up on top. Now for the room-sized chamber, we used our 20-meter cube stainless steel chamber that has been in our lab for a long time. We ran many experiments on it. Chamber is also fed with, in this case, is outside air that is pre-filtered through a carbon bed and chemisorbent to reduce the VOC levels to a minimum. In the case of formaldehyde, we still have a 1 or 2 ppbs background level. So that's our baseline. It goes into a chamber, and then there is an exhaust. Let me show the exhaust here. So we have a controller exchange rate in the chamber. We have a couple of fans. And we also installed an external loop through which we would recirculate the air from the chamber multiple times through a filter. So the filter was placed on that here on the filter holder. And we used a variable speed fan and an iris damper to both adjust and measure the flow that was going through the recirculating loop. Now, inside the chamber, we had 3 humidifiers, and the number 3 was just because in order to reach the level we wanted, one wouldn't do it, so we had to do more than one. And the 3 were connected to an RH controller, so we would set the RH on the controller, and the controller would turn on and off the humidifiers to maintain the humidity at the value that we wanted for several days. Okay, I think I have photos for the chamber too. This is exterior of the chamber. You can see there the exterior recirculating loop, the filter holder, the variable speed fan, and the damper. And then this more detail here shows the sampling ports downstream and upstream from the loop. Similar to the previous setup, what we do here in every case is to take samples upstream and downstream simultaneously. And I have another photo from the inside of a chamber, just so you can see how it looks. We have the ductwork that brings the air all the way to one of the corners of the chamber, and then we have the 3 humidifiers there and the fan. So in both the bench scale and the room setups, the analysis we ran was the same. We were collecting formaldehyde samples using the very well-known traditional EPA method, consisting on a small cartridge through which one can draw actively a certain volume of air. We ran it for about an hour at a liter a minute, so we collected about 6 liters of air. And the cartridge contained this compound called DNPH, dinitrophenylhydrazine, adsorbed on silica. This is a reactant that is very specific to carbonyls. Formaldehyde and every other carbonyl would react with this compound, form this stable derivative that is called a hydrazone. So by doing that, because it's a much larger molecule, it is retained in the cartridge rather than going through the cartridge. And also, after it's extracted, it can be analyzed by HPLC, and it's a very simple analysis, and it provides very good limits of detection of about less than 0.1 microgram per meter cube. So it's a very sensitive method, easy to operate, and fairly well validated. So that's what we have been doing for this project. So let me show you a little bit what we learned. These are some of the samples we ran on the bench scale chamber. The top figure corresponds to the filters that were purchased from retailers, and the bottom figure is filters that came directly from the production line. And in each of them, both of them are run at relatively high humidity, 60-some% relative humidity. And in both cases, we have 2 clusters of data, one corresponding to 24 hours, and the next one is 48 hours. The reason for this is, we didn't know exactly how long to run this, so after testing several conditions, we realized that, we had to be run for a while, so we equilibrated the filter for 24 hours at constant flow, constant humidity and temperature, and we took a sample at the end of those 24 hours. But then, to be sure, we ran it for another 24 hours and took another sample, which we call here 48 hours. That was a method used in every case. And as you can see here, if you compare, let's say, each material the value for 24 and for 48 hours. There was, in all cases, there was a decay. Sometimes it was a small change. In some cases, it was a larger change. But overall, we see that after 48 hours, we see a lower concentration than at 24 hours. So, but before we go into that, into more detail, let me also mention here another important difference that we observe, which is fiberglass versus synthetic. The synthetic filters are the very little bars here. Let me see, where are we? Here. So these two here, 3.7 or 4, and then going down to 2.8 to 3. Those are the two synthetic filters. A couple of ppb's emission, nothing else, versus somewhere 20 all the way to 120 for the other filters, for the fiberglass filters. So one thing we learned is, and then the color coding, and we will use the same color codings along this presentation, so I'm going to introduce it here. Remember I mentioned we took filters from the 3 manufacturers. So manufacturers here are called A, B, and C, but also we use the color, so I would call them blue, red, and yellow, just because it's easier to spot easily on the screen. So the blue, red, and yellow in this case are the 3 different manufacturers from fiberglass filters for homes, relatively same size, same dimensions. And we see fairly different emissions. The blue, in this case, is much higher than the red, and the red is higher than the yellow. So that is one. There is I have 2 blues, in fact, because I'm showing here a second filter from the same manufacturer, which was also fairly high, much higher than the very first one we tested. I'll get back to that later in more detail. And now for the bottom figure, in the bottom figure, what we have is the 3 filters that came directly from the line, and those were initially a lot higher. The concentration was a lot higher, but also it dropped much more when we looked at it on the second time. So in principle, it looks like the curing process here either was not fully complete, or it was just simply the polymer was fresher here, and it led to an initial plume of higher emissions, but that plume decreased faster as well. Just taking 24 over 48, just the ratio, and we see that for the bottom figure, the filters that came from the production line, we had about 46 to 50% drop in the first 24 hours. The other filters, the drop was much lower. In some cases, were almost negligible, 2.5 here. But in general, most of the filters changed by about 24%, 25%. So, and this is at high humidity. Then, of course, we measure this at the lower humidity. And what I'm showing here is 2 effects. What I'm showing in the same slide, and now focusing only on fiberglass, because we saw already that synthetic doesn't emit very much. So we let the synthetic filters alone for a while. The fiberglass filters, when analyzed, what we did in this case was we took the same filters, not strictly the same exact filters, but filters from the same box 6 months later. So these usually come in a box of 10 or 12 units. So for each of these tests, we were using 2 units. So what we did here is 6 months later, we took another couple of units from the same box and reanalyzed. And by doing that, what we found was that just from sitting in our lab at moderate moisture and temperature and no light, very common storage conditions, in 2 of 3 cases, the concentrations that we measured dropped quite significantly. In the first case, the drop was 20 to 30%. This case was more like 65 to 75%, quite significant change. Now, this filter, which was already relatively lower, did not drop very much. So we see that in these 3 sets of filters that we were looking, we probably were taking different snapshots of different moments of the much longer trends that have to do with the the curing and the setting of the polymer, and how this, the same challenge in terms of moisture leads to different levels of emissions, formaldehyde emissions. And that was actually quite interesting to see, because in the end, it's not a matter of one manufacturer producing a higher emitter and another one producing a lower emitter. It's more rather than, depending at which point of the curing process you happen to have your filter, emission could be much, much higher or a lot lower. In all cases, it is still significantly higher than the synthetic filters, but the range of variability was huge. Same filters now, when run under the same conditions at 34, 32% relative humidity, concentrations now are much, much lower. Not negligible, but much lower, and that's what's shown on the final set of bars, always for 24 and 48 hours in this experiment. But you see the decrease is somewhere between 65 and 80%. So what we are seeing here again is that fiberglass, the presence of fiberglass combined with high humidity is what leads to these significant emissions. And the final test we did on the small chamber before bringing these filters to our more realistic larger chamber is the following. We took some of these filters and we cut out carefully the frame. So we separated the media of a filter from the frame the best we could. So we tried not to leave any fibers on the frame and try to keep all the media together. And then we ran a test with just the media and a test with just the frame and compare that with the test of the whole filter. And remember, our advisors told us that don't worry too much about the frame, because the frame is cardboard, it shouldn't emit very much. And in fact, what we found was exactly the opposite. We found that the frame alone was as strong a source as the media in the 3 cases we looked at here. And even more, in the blue case, in the one I show here first, it's almost like you have good mass balance. If you add up what we measure from the media and what we measure from the frame, gives you roughly what we measure for the full filter. In the other 2 cases, it's not like that. If you add up the media and the frame here on the yellow one, you don't get exactly to the level, you get below that. And then on the red one, you get a little bit above that. But this is not that quantitative, really. So we had to look at more of in qualitative terms. In qualitative terms, what we see is that both the media and the frame seem to contribute at the same level. And I don't think it is the cardboard itself. The cardboard, I don't think if you put a piece of cardboard in the chamber, you'll see these kind of emissions. I think the cardboard is embedded in the polymer, because that's where the media is attached to the frame. And if you remember handling these filters, the cardboard is kind of rigid from being almost covered with a layer of this glue, or frankly, I don't know if it's the same exact polymer that is used to keep the fibers together as to attach the fibers to the cardboard. So that is a question we can't really answer. But what we do see is that emissions are coming from both components. Okay, so with that in mind, then we selected these 3 filters, what I call here the blue, yellow, and red, and 1 synthetic, which is going to be shown in green. And with those 4 filters, we ran now our full-scale room-size chamber study. So here is the bulk of our data for the room-size chamber study. The top figure is measurements that were done at the moderate humidity, around 40%. And the bottom figure are data that were measured at the higher humidity, around 70%. Each bar corresponds to a 24-hour sample, similar to what I showed on the small-scale chamber. So we equilibrated. In this case, we were running air through the filter for 24 hours before taking each of these data, each of these samples. And then what we did was we took a sample, we continued running for another day, took another sample, and what we did in the chamber was we evaluated 2 different flow rates or recirculation rates in the loop, which correspond to 2 different phase velocities on the filter, which are in the range of values that are typically found in the HVAC system. So the striped bars here correspond to the lower phase velocity, and the solid bars correspond to the highest phase velocity. So in summary, for each of the filters, we did 4 measurements, 24-hour each. So it's a week-long test. In each case, we started on typically on a Monday. We let it run for 24 hours. We took a sample, another 24 hours, took another sample, switched to the higher recirculation rate, let it run for another 24 hours, took another sample, and finally took a second sample under the same condition. That was our experimental matrix. So on the bottom figure, what I see here is that what you see across both figures, you see what is our chamber background level for formaldehyde. This was measured separately, and we know that for many, many years of experiment in the chamber. So when we work at the low relative humidity, really the filters don't contribute very much. Both the synthetic and the fiberglass filters contribute maybe 1, 2 ppbs. The red filter, as you see, is one that is a stronger source in this case. And I should say, oh, I forgot to mention something. When we saw the aging effect on the small scale chamber, we saw that just by storing those filters in our lab, we would lose a significant fraction just from keeping them around. We decided to buy the same exact filters, but buy them again for these tests. So the filters I'm showing here are exactly the same, the same brand, the same model, etc. But this is a different box that was bought maybe a year later. And what is interesting here is that if you remember, the blue filter was much, much higher than the other ones on the first set that we bought, but not on the second. And on the second set that we bought, it is a red filter that happens to be the one that is the highest emitter. And here again, I have to say this, to me, has to do with the history of the filters, which we really can't know. I mean, once we order them, who knows how many months these filters have been stored in warehouses, under who knows which temperatures, humidities, etc. So there is a whole history that has a lot to do with the actual emissions that we measure. So in these particular cases, it's interesting because we took the same exact brand and model, and we bought a different box a year later, and the order in which they were emitting was quite different. So that said, we went ahead with experiments, and what we found was that at the high humidity, we found also that the synthetic filters, if you see here on the bottom figure, synthetic figures remain at a couple of ppbs above. So there may be some glues or something on those filters that contribute a little bit, but it's a small contribution. The fiberglass filters contribute much more. And at least in the case of a blue filter, we saw quite good consistency over the 4 data points we had. We were happy with that. With the yellow and the red data points, we weren't that happy because we see that there is it looked like almost like in 24 or 48 hours, we didn't quite reach a steady state. So we decided to do additional measurements just to be sure. So on those two, we did for the yellow one, we did, I'm repeating here the 4 data points I showed before, and these are 2 additional ones. So at least here we had 4 data points at the high air flow velocity, and we were sort of convinced that within the error bars shown here are just the error of a duplicate determination, which is very little because that has to do with the error of the DNPH method, which is very small. But we found that there is a lot more fluctuation and variability in just taking the same sample one day to the other. So that's why in the end, the error we will consider is the error associated with these 4 data points. And for the red filter, it's even more. As you see there, we have quite a range of values, although most of them are in the order of 50, or sorry, of, what is it? Yeah, around the 50s. But there's a couple of them that went up to 70, one that was down to 26. So it is fairly variable. And the other thing I noticed is that the red filter, which is the highest emitter, is also the one that has the highest variability, which is not surprising. So with this information, the next thing we did was determine the emission rates. So we had to come up with an emission rate expressed in micrograms of formaldehyde per surface area of filter per unit time. And in order to do that, we took the change in formaldehyde concentration in the chamber, and we multiplied by the chamber volume, the air exchange rate, and divided by the area of the filter. Very simple. And that's how this was done for both the moderate RH and the high RH. This is what data shown here is for the moderate relative humidity, and if you see the values for fiberglass and synthetic are not that different here. So fiberglass only becomes a strong source at high humidity, but is comparable with synthetic at low or moderate humidity. Now, when we go to high humidity, sorry, I skipped one here. When we go to high humidity, synthetic filters continue to be at the same level of just a couple of hundred microgram per hour per square meter, but fiberglass increases by an order of magnitude. So now there are 500 to 4,000 of the same units. And that is, I think, just confirming in a more realistic setting what we have seen before. So this is our, let's say, the raw experimental data, and with that data, we try to come up with some modeling to predict how would this impact our exposures in the home. So the first thing we did was to compare our emission rates with other emission rates that were determined in the literature previously. The data in the left is from a study by Kelly et al. A couple of decades ago, and these are measurements done in a small chamber similar to ours, the bench study. And this is for a range of different products. The first two on the left are composite wood products. Remember, those are high emitters. Compare with that, fiberglass products, and in that study was ceiling tiles and insulation, not filters. Fiberglass products were somewhere not as high as bare wood products, but comparable to coated wood products. The second group is our own study from 2013. And remember, our own study was fiberglass filters used in commercial buildings, which are thicker and larger. And those are consistently higher than the measurements we determined in this study for the home filters. But our data for the home filters are not that different from the fiberglass data from the Kelly study. So overall, I think we are satisfied with a general order of magnitude of our values. I think we are in the right ballpark. And remember, here we have each bar there corresponds to, in our case, 3 different fiberglass filters that each of them had a range of values. So it is a fairly wide range of emissions. So with this information now from our work, what we did was modeled concentrations of formaldehyde that would be produced in 3 different homes. We took a small apartment, a mid-size house, and a much larger house. And in each of these 3, we took 2 different scenarios. And the scenarios are based on the size of the filters. Because we ask ourselves, okay, what is a reasonable size of a filter? I know. I went and measured the filters in my house, and that gave me 1 data point. But then I looked in the literature. There were a couple of studies showing, with that information, both the filter size and the floor plant. And from just that limited amount of information, what I took was this. I came up with this parameter phi here, which is the ratio between the filter surface area and the home floor area, which is somewhere, for those limited studies I saw, is somewhere between 2.4 and 4 times 10 to the minus 3. And I took those 2 as the 2 extremes, and then for each of our 3 homes, I evaluated those 2 extremes. That would be a home with a relatively small amount of filter and a home with a larger amount of filter. The equation is very similar to the one I showed before. In bursts, now I have our data is emission factors. I want to back calculate what would be the contribution. Delta C is the not the absolute contribution because there are multiple sources, but this is how much formaldehyde is provided by this source, by the filters. Multiplied by the filter area, divided by the home volume and the air exchange rate. This is super simple, I mean, it's overly simplistic and obviously can be done in a much more complex way. But this is just to give us a back of envelope idea of what would be the contribution. And we did that for a number of conditions. This is a subset of conditions. And I apologize, the slide has tiny numbers, but I still wanted to show all 9 of them together because this gives you an idea of what are the main parameters here. From the 6 scenarios, I'm showing 3 here. The first 2 are our smaller apartment. ARV1 is our tiny apartment. ARV2 is the mid-sized house. So the first 2 are the smaller apartment with a small amount of filter and with a larger amount of filter. That is our phi parameter, lower and higher. And then the bottom row is our mid-sized home with the higher value of a phi parameter. And then the first column is a moderate humidity. And at moderate humidity, things are boring because there are not really very much formaldehyde being emitted. So we just calculated that to check off and say, okay, if you are working at 40% humidity, don't worry, these filters will not be a problem. We just confirmed that. And this is also done for the air exchange rate 0.2, which is fairly tight. So that means that's the worst possible, close to the worst possible condition for the moderate condition. And in that case, we only see somewhere between, I don't know, a fraction and 1 or 2 ppbs added to the indoor air. So it's not a big deal. Now, the second and the third column correspond to 70% RH. And in those cases, we have with 0.2 air exchange rate and 0.5. And here, let's focus on the lines that cross these bars. Those lines are our reference, which is the OIHA reference exposure level for formaldehyde, which is 7 ppb. And also, we wanted to compare with our proposition 65 level, which would be much lower. This is for cancer, so obviously it's much lower. And it's a chronic exposure of something like 2.2 or so ppbs. And what we find is that now when we are working at 70%, there are some conditions where some of these bars, if not all of them, cross, well, all of them tend to cross the lower bar, the Prop 65 bar, but a good number of them cross the OIHA 7 ppb bar. And that means that there are situations in which one can see these filters contributing a significant concentration of formaldehyde to indoor air. Now, let's keep in mind that this calculation is based on filters running 24/7, and that is that's not the case in most homes. Most homes, the air conditioning or the heating is not running all the time. It's running intermittently. You know, it goes on and then it goes off again. So in order to do a more realistic prediction, we need to now multiply these values for a factor, and that factor is a fraction of the time at which the air is circulating through a filter. So how do we do that? Fortunately, our colleagues at the lab a couple of years ago had published a very thorough study of precisely this, how to calculate the duty cycle, the fraction of the time that the HVAC is working and this was done not just for California, it was done for the whole US, for a variety of climate zones. So from this study, what we did was we adopted a very simple linear correlation between that fraction of the time, the duty cycle, and the delta T, where delta T is the difference between outside air temperature and the thermostat setting, which is 65 Fahrenheit for heating and 78 for cooling. So, and that delta T is something that we can then easily obtain from data because outside air temperature is very easy to obtain. And well, I'm showing here just one plot from their study. They did this for different house vintages, and you see that older homes tend to be more leaky, so they have more of a different slope. I just use the average slope in this case. So for outside temperature, what we did was we went into PG&E report, recent report has very good data, and we took from the 16 climate zones in the state, we just took half of them. We looked at either highly populated areas, Los Angeles, San Francisco, etc., the Central Valley, and also the extreme conditions. We went to Eureka, which is very relatively cold and humid, or Brawley, which is down in the south and is very hot in the summer, and also Bishop up in the Sierras, which is the coldest winters. So we try to sample all those conditions. Let me show you just for Bishop, which is an extreme cold condition, the kind of data that we obtained from this PG&E study. It shows the average temperature for both the daily average, but also the peak highest and lowest as a monthly average. So we took, from that distribution, we identified which is the coldest months for heating and also the warmest months for cooling. And in this case, I'm showing, well, both, but for heating clearly in Bishop is what predominates. The average temperature leads to a duty cycle of about 37%. That means even in this extreme location, in the middle of the winter, if you take the daily average, the heating is working, air is circulating through the heating only a third of the time. Of course, if you go to the middle of the night, which is the lowest temperature, then it's going to be running 2/3 of the time. But even in an extreme case like this, it's not running all the time. So we did this analysis for every of these zones, and then we came up with this table. The table has for the red heading here is the heating season, and the blue, the cooling season. And we could get from the average, from mean values, we took, let's see, if we just focus on the column here, the hourly time fractional for the mean for heating, we see, for example, for Bishop, the 37% I mentioned before, and this is the highest. And it goes all the way down to 10% for LA. So that means winter in LA, the air is running through, in average, through the day, is running only 10% of the time, which is mostly during the night. During the night, it would be more like a third of the time in LA, 2/3 of the time in Bishop. It's interesting that the peak of the heating season is always January throughout the state, but the peak of the cooling season is mostly July, but obviously the Bay Area is September, as we know. Our summer is in September, and LA is in August. So with this data, what I did was I applied this to the values that I mentioned earlier, and then we came up with a predicted formaldehyde contribution from the filters running under more realistic conditions. And I will go to that in a moment, but before I go there, let me show you something else, which is we need to know what is the humidity. Okay, we know now the fraction of the time. Now we need to know what is the humidity. And so what is the humidity under each of those conditions in those locations? We have two sources. We have outdoor air as a source of moisture, and also we have indoor sources. So for outdoor air, when you look at the data, for example, in winter, in most of these locations, the outdoor air relative humidity tends to be fairly high, up to sometimes 90% or so. But that is mostly because the temperatures are low. When you take that mass of air and bring it into the house and heat it to 65 Fahrenheit, that same moisture becomes a lot lower relative humidity. So I'll come back to this slide. Let me go to the next one just for a second. So to illustrate that more graphically, this is a psychrometric chart, which is something like a phase diagram for your building. So on the x-axis, you have the temperature. On the y-axis, you have the absolute humidity, not the relative humidity, the absolute. And then the curves are the relative humidity. So if you keep absolute humidity constant, you bring cold air into the house and heat it. That's what you're doing with these red arrows there. And it's different for each location, but in all cases, you go from relatively high relative humidities outdoors to much, much lower relative humidities indoors. In all cases, below 40%, which is the line that is marked in orange there. So that means I don't think outdoor air would be a significant source of moisture. So if we think that just because we are in I don't know, up in Eureka, which is very humid, we will have a problem with filters emitting a lot of formaldehyde. Not necessarily, because it all depends on which is the temperature of the air when it hits a filter. I guess if you have a system in which a filter is directly in contact with outdoor air, then might be. But then we have to look at, usually the filters tend to be on the inside of a building, and they're at the same temperature as the indoor air. So I guess in most cases, the outdoor air will not be a source of moisture. And that is true for the winter. It's also true for the summer. I could not show a similar plot here for the summer because, as we all know, when hot air goes through the air conditioning, the excess moisture gets condensed as liquid water, and that liquid water gets just drained out of the system. So it is also removed. I mean, it is removed from the air, and we are not going to be exposed to that. And it's more difficult to calculate, so I didn't want to show it on a plot like that. But I mean, in both cases, winter and summer, we shouldn't expect outdoor air to be a significant moisture source. And that's why we didn't need to look at indoor moisture sources. And certainly our own activities and our own presence becomes a significant moisture source. And I have here in the table on the left an example from one study showing for a family of 4, a number of activities related with release of water and a number. So we came up with a number from there, which is 12 liters or kilograms per day of water that gets evaporated into indoor air. If we take that number and then we bring it into our model homes using the two air exchange rates that we are using in our models, what we see is that if we consider the mid-size or the large home, that is RV2 and 3 here, the contribution of that amount of moisture being released into the indoor environment, again, is not a lot. It's somewhere between, 4-8 in the lowest case, up to maybe 40-45%. Only in the small house. So that means you need to have a family of 4 living in a small apartment with a relatively small air exchange rate in the winter. So you see, we are starting to add up 4 or 5 conditions here. Then you start having high levels of indoor relative humidity, and then you're in a situation in which you can have high emissions from a filter. So there you go. You need to have at least 4 or 5 conditions happening together for these emissions to be significant. One final comment here, we are neglecting, this is an oversimplification again, because we are neglecting indoor sinks. Moisture is not only emitted into the air, it also can condense from the air into, a cold window or any cold surface, and that can be a way in which the relative humidity can decrease. So we are assuming that those things do not exist here. So finally, what I have here, based on all of these considerations, what we did was, okay, let's look at 2 different scenarios. One is which we have all the possible bad conditions together. What would be the contribution of these filters to indoor air? And here's what we got. This is a family of 4 living in this small apartment at 0.2 air exchange rate. That is very tight kept apartment. In the winter, so the thermostat is running at 65 Fahrenheit. The duty cycle will be determined on where this apartment is. So we did this calculation for the 8 locations that we evaluated, which is shown in the histogram here. And we are, with all the assumptions I mentioned before, no sinks for moisture, considering here only indoor moisture. So we actually have more moisture coming from outside there. So this is, again, a simplification. And each of these bars add up the emission ranges from the 3 filters, the 3 fiberglass filters I showed before, the blue, the red, and the yellow. So taking all of that into consideration, we see that in 3 of our 8 locations, we could exceed the OIHA 7 ppb chronic reference exposure level. And that is in Bishop, in, where else? Stockton, and Fresno. There are 2 more locations where we don't exceed, but we are fairly close. So if we start adding other formaldehyde sources, you would be exceeding that for sure. and those are San Francisco and Eureka. And then the other 3 locations are not negligible. It's just 3 to 4 ppbs. So we see that, yes, it is a function of the location, but in all cases, the contributions are not negligible. And again, that is the worst case scenario. Now, the more typical scenario, which is shown here, for the more typical scenario, the only change I did was just the size of the home. This is just the mid-sized home, not the tiny apartment. So just by diluting the moisture and by having, therefore, lower relative humidity, you are now in the situation in which emissions are much lower. And in this case, we only predict a fraction of a ppb. So in every location, this is not an issue. So I think with that, I would like to maybe go to our conclusions, which is, first of all, we confirm that for the residential fiberglass filters, we see the same general trends that we have seen for the filters that go to commercial buildings. We also observe emissions from the media and also from the frame. This is new from this study. We hadn't done that before. In the majority of cases, we think that these filters will only provide a tiny or small contribution to indoor formaldehyde, so it's not going to be a problem. But there are situations in which you may have higher concentrations, and those are the ones I showed before. What about source control strategies? There are a couple of ideas that could be easily implemented. Well, not so easy, but one would be for industry to replace this polymer with something else that does not emit formaldehyde. That is obvious, but it's also obvious that it's not cost effective, or at least it's not something that industry is ready to do. So there is a cost barrier there, and it's unlikely to happen. If you go to a supermarket or Home Depot or any store, go through the aisle, fiberglass filters cost $1 or a few dollars. Synthetic filters tend to cost, depending on the rating and the quality, could be somewhere, I don't know, 5, 10, 20 or more. So there is a significant price premium. And considering that together with the fact that the exposures are more significant in smaller apartments that are more crowded, you start having there what could be even considered something like an environmental justice issue there. Because, I mean, it's definitely something that is easily solved if you have money to buy a better filter or if you live in a larger home. So then, of course, the other source control strategy would be replacing your filter and using another type of filter. I just want to finish with mentioning a number of limitations of this study. One is that we only could look at a few conditions, a few types of filters, phase velocities, etc. Only 2 RH settings, which is what we call moderate here, around 40% and high around 70%. It would have been great if we knew this earlier, that to span more the range in between them, because it's not linear. The way emissions increase is more exponential. So we need to have more data to describe that if we want to do more accurate modeling of this. This could be done later, but we didn't have time to do that on this study. I think we did a good job covering different climate zones in the state, but of course, California is very mild climate overall. So if we want to expand this to the US, there are both warmer and much colder areas that should be considered in modeling that we didn't do here. And the other thing is, all the work I'm showing here is with brand new, out-of-the-box, clean filters. And you know, the filters run for about 3 months or more. They start building up dust and particles, what's usually called filter cake. And that probably has 2 effects. One is an effect of the polymer being degraded over time and probably emissions going down with time, but also the filter cake has an effect. And we have seen a little bit of that in a previous study that we didn't have time to go into more details at the time when we did this study, but this is just showing a study in which we did expose filters for 3 months at 2 different locations. This is just taken from a paper we published in 2011, and I'm closing with this to illustrate the possible effect of filter cake. The unexposed filter, you see, emissions are a lot lower than the filters that had been exposed for 3 months. And even more, these are identical filters, but one was exposed in our building, Del BNL, and the other one was exposed in the Port of Oakland to different particles, one more sooty and ours was more vegetative debris and things like that. And clearly there are contributions that could be either coming from a buildup of moisture at the filter cake that facilitates the degradation of a polymer, or just the filter cake itself could be a source, and we don't know that because it's a complex mixture and we haven't had the chance to study very carefully. So with that, I think I'm going to finish here. I'm going to thank you very much for your attention, and I'm sure if you have any questions, please let me know.
Yeah, thank you very much, Hugo, for the great talk. And now we're going to have a Q&A. I haven't seen any questions from online audience, but if you're watching the webcast and have any question, please send your question to the email list on your screen, which is sierram@calepa.ca.gov. And we're going to start from a question in the room. If you have any question, raise your hand. I will bring you the microphone.
Hi, Hugo. Nice talk. Thanks.
Thank you.
I had a question about the duration that the filters could sit before, say, they decay maybe all the way down. It looks like there's certainly a drop. So any speculation on how long they might sit before you really get a benefit from having them off gas?
Yeah, well, that is a good question. And also we had the idea about the long-term decay when it's in the box, which we did for about 6 months or so. And then the short-term decay when it's running on whether it's 2 days on our small chamber or 1 week or more, actually, one of the filters ran for 2 weeks in the larger chamber. And at least in that case, we could see that for 2 weeks, emissions were, if you remember, let me go back here. Here. No, sorry, here. The red histogram. The first 4, this is a week, and then I guess we have 2 more weeks there. And this is continuously running at 70% humidity. And then the same filter, so it went down and then up again. So there is some fluctuation, but I don't think that we will see a direct, decrease going down to 0. What we saw in the smaller chamber is probably an initial higher than normal emission in the first 24 hours. But then my sense is that the 48 hours is what really would be what you continue to see for a longer time. Unfortunately, we didn't do that for much longer in the smaller chamber, which would have been nice. But yeah. Well, we did this for 3 weeks and it didn't go to 0. So at least in one case, we didn't see that. And 3 weeks is a significant fraction of, the lifetime of this filter is 3 months. So it's about, 20% or so of the lifetime. And also this is in a very clean chamber, so there is no buildup of particles on this filter, which is also unrealistic.
Any more questions from the room? Okay, I do have a question. So based on your experience searching the filters online and in the market, is that right? Most of the fiberglass filter are like low MERV filter, and like synthetic are more like high MERV rate filter. Well, that means like if we switch from low MERV to high MERV filter, it may take care of the formaldehyde issues automatically by itself?
Yeah, absolutely. These fiberglass filters that you, at least all the ones I've seen, there may be others, but all the ones we have seen when we did the initial search and we bought this longer list I showed at the beginning, these are fairly low efficiency. You can see through them. And I just been to a seminar a few weeks ago from Professor Bill Nasaroff in campus, and he had this pretty interesting observation, which I totally agree with. He said, if you can see through a filter, it probably doesn't do a very good job in removing particles. It does good in maybe retaining larger, hair or larger particles. It protects the equipment. It protects your HVAC system. It doesn't actually do much protecting people or cleaning the air. So that's my sense with the fiberglass filters I've seen. Obviously I haven't seen all of them, but the ones we see, the ones we have seen, the ones we use for this study for sure.
Thank you. Sure.
So the pleated synthetic filters are a paper material or a polyester material? I'm wondering, based on the filter cake that looks like it could build up over the 3-month duration of the recommended use of a filter, at the end of that 3 months, even though the synthetic or the polyester filter looks like it's clearly better than the fiberglass, at the end of the 3 months when the filter cake's building up, it seems like that the synthetic may end up being a source as well. Have you looked at that?
No, we haven't. That's an excellent point, and we haven't looked at that in this study, mostly because the way this study was designed was limited and focused on the initial emissions from brand new filters. But that is definitely something to explore further. And it's interesting both for home filters, but for commercial filters as well. This small amount of data I showed now at the end, that was a byproduct of a study in which we are looking at something else. In that study, we were looking at the reactions of ozone with the filter cake. So, and by serendipitously, we found that suddenly the formaldehyde was much higher, and that was completely unexpected. We didn't know why, how to explain it, and we had these two possible explanations. If it is that the filter cake serves actually as a capacitor for moisture and accumulates moisture, then in that case, maybe the fiberglass filters will continue to be a much higher source than the synthetic filters. But if it is the filter cake itself that degrades over time, then I agree with you. Any filter would become a source. And that is something that is completely worth studying, and we should do it. We should do it for sure.
Okay, we do got one question from online audience. So the question is, why did you do 24 and 48-hour study as opposed to longer study, similar to the study as shown in your introduction slide?
That was for practical reasons. We had to screen a larger number of filters. That study that I showed at the end, we actually, in that study, we didn't look at the evolution over that period of time. We simply exposed filters for 3 months. We just installed them for 3 months, and then we brought them back to the lab after 3 months. And it's a different experiment. In this case, we focus on the initial emissions.
Thank you. Any more questions? Okay, with that, I think we will conclude, and thank you so much for your great talk.
Thank you very much.
Thank you.